Okay, so hi guys. In this video, we'll discuss the second derivative test for relative extrema. Let's get started. So first, let's recall the test for concavity. So let f be a function whose second derivative exists for all values on an open interval I. So if f double prime of x is greater than 0 for all x in that open interval, then the graph of f concaves upward on I. On the other hand, if f double prime of x is less than 0 for all x in I, then the graph of f is concaving downward on I. So of course, this is a really helpful test when you want to identify the behavior of a curve just by utilizing the second derivative of a function. Next, let's recall a point of inflection. So a point of inflection is defined as the point where concavity changes. So it's either your function was concaving downward and then it started to concave upward, or vice versa. And then if the pair C and f of C is a point of inflection on the graph of f, then it follows that either f double prime of C is equal to 0 or f double prime does not exist at C. So with all these concepts, we are now ready to define the second derivative test for relative extrema. So this is the second derivative test for relative extrema. So let f be a function such that f prime of C is equal to 0, and the second derivative exists for all values on an open interval that contains C. So if we have f double prime of C be greater than 0, then it follows that f of C is a relative minimum on f. On the other hand, if we have f double prime of C be less than 0, then it follows that f of C is a relative maximum. Take note that if f double prime of C is equal to 0, the test fails. That is, if f may have a relative maximum, a relative minimum, or neither. In such instances, one can use the first derivative test. So let's apply the second derivative test in this problem. So consider the function g of x, which is equal to x cubed minus 2x squared minus 5x plus 6 all over x squared minus 9. And then we're asked to do the following tasks. Let's do the first one. So we'll first find the critical points of g. So take note of this hint. We're going to need it in a while. So of course, in order to get the critical points of g, we first have to get the derivative of g prime of x. We have to get the derivative of g of x. So we'll get g prime of x. So we'll apply the quotient rule. And then if we want to further simplify the expression, we'll get this expression. And then we'll further simplify this expression. And then take note of that hint that we were given a while ago. So we'll factor into this. And then we'll be able to cancel out like expressions. We'll get the following final expression. And then of course, a critical point is when g prime of x is equal to 0 or when g prime does not exist at x equals 0. So if we set g prime of x to be equal to 0, we'll get x equal to -1 and x equal to -5. So these following values are critical points of g. You might be wondering why x equals -3 is not the critical point of g. That's because x equals -3 is not part of the domain of g of x. That's why we only have -1 and -5 as critical points of g. So now we'll move on to the next task, and where we will use the second derivative test to find relative extrema and to determine if the relative extrema is either relative maximum or relative minimum. So if we take the second derivative of g, we'll get the following. So of course, we'll apply quotient rule again. Then we'll simplify further. We'll cancel out like terms. We'll get the following. So this is the second derivative of g of x. And then we evaluate the second g double prime of x at the critical points that we got in letter A. So first, let's apply x equals -1. And then you'll get the following value, which is 1. And of course, 1 is greater than 0. And it follows from the second derivative test that g has a relative minimum at x equals -1. Next, if we evaluate the second derivative of g of x at x equals -5, we'll get the value equal to -1. And of course, -1 is less than 0. Hence, using the second derivative test, we'll get that g has a relative maximum at x equals -5. Okay, let's do the final task, and where we will determine all possible points of inflection of g. So of course, in order to get the possible points of inflection, let's set g double prime of x equal to 0, and then we'll get that. However, once we do some manipulation of the equation, we'll get that 8 equals 0. And of course, that's not possible. So therefore, g has no points of inflection. Okay? Yeah, I think that's it. Thanks, guys, for listening.